Okay, for the International Conference on Innovative Technology, Engineering and Science 2020, the title of this research is a wearable textile antenna using of clothed iron for the indoor wireless remote monitoring. So for the introduction, the research is mainly focused on the integration of the electronic circuit onto the textile, which is the new evolution of the Internet of Things. So from this figure, we can see that this elderly was equipped with the sensors, where this remote monitoring requires that this device must not affect the elderly's regular habits in telehealthcare communication. So the combination of the non-invasive wearable sensors and the technology of information will allow this elderly to receive the needed assistance while continuing to live in their own home rather than expensive nursing home. So by having this kind of a research background, we come up with the new title of the low-cost textile antenna. Nowadays, there are so many textile antenna in the current technology which is used for the garment. The first picture, we can see that this textile antenna is attached to the fabric. The second figure also, we can see that the textile antenna is glued or attached to the garment of the patients, and the third one is used by the firemen. But however, this design shows the size is really big. So the existing design don't always provide a reliable link between the receiver and the transmitter, since they have a rigid structure and a narrow bandwidth. And some of the material used for the textile antenna have expensive material and high cost technique. And also there are also limitations where this once the textile antenna is washed or scrambled, so the performance of the textile antenna will be reduced. So for this research design, this is the dimensions of the textile antenna, which use the coplanar waveguide to substitute the ground to make sure that the ground was on top of the textile. And the step impedance is used to substitute the patch antenna, which is resembled by the element of WP1 till WP5 for the width and LP1 till LP5 for the length. So for the technique that have been used is by using the thermal print using the clothed iron. So the antenna process flow start with the ink cartridge modification, and then there is a transfer of the conductive ink to the printer, while the printer now is used to print the antenna design on top of the absorbent heat paper in C, and then the design now is being transferred to the fabric by using the manual thermal using iron clothes, which is affordable to all the users. And the SMA connector is connected to the feeder of the antenna in E, and F is the overall illustration of the antenna on the fabric. There is also continuity test on the antenna has been performed, and the flexibility test due to the bending and the stretching tests in figure 4. So for the results, we can see that this antenna managed to transmit the signal with a high percentage of the transmission, which is below than minus 10 dB for the return loss S11 parameter. And then they have a gain of 3.81 dB, which can be seen from figure 6. Okay, and the textile antenna also is already been tested for both the part. The first part is by having it as a transmitter module. The first block diagram, we can see that this developed prototype textile antenna was connected to the transmitter with the mini camera, while the receiver are connected to the TV display to show the performance of this textile antenna. And then the second testing is a textile antenna as a receiver module. So the first one is the test connection flow, where this textile antenna is connected to the receiver of RC832 and the TV display, while the transmitter is using the TS5828, which is connected to the mini camera. So for the conclusion, we can see that in this research, a low-cost textile antenna has been designed on the cotton substrate by using the manual transfer of clothed iron at 5.8 GHz. The material used for this textile antenna is a conductive carbon ink. So the textile antenna shows significant results of the return loss, gain, bandwidth, and the directivity. And it also shows the remarkable surface and consistent RF performance after repetitive flexing and stretching tests. And it is also tested using the transceiver module, which can manage to receive and transmit the signal up to 3 meters, which is make it suitable for the low cost.
The antenna was first tested using AV transmitter to transmit an AV signal to the AV receiver. The AV receiver, which has been fixed to a television to display the receive AV signal from the transmitter. This is the prototype of the textile antenna as the transmitter. When tested, the antenna is able to transmit 3 meters away without any signal loss from the AV receiver. In the test TS5828, a 5.8G model transmitter used to transmit the signal. For the second test, the fabricated antenna was fixed with an RC832 receiver to receive the AV signal. This is the prototype of the textile antenna as the receiver. The antenna connected to the receiver, and the transmitter brought further away. In the test, the distance ABLE receives by the fabricated antenna is 3 meter.